The lead-acid battery was invented in 1859 by French physicist Gaston Planté and is the oldest type of rechargeable battery. Despite having a very low energy-to-weight ratio and a low energy-to-volume ratio, its ability to supply high surge currents means that the cells have a relatively large power-to-weight ratio. These features, along with their low cost, makes it attractive for use in motor vehicles to provide the high current required by automobile starter motors, as they are inexpensive compared to newer technologies. Lead-acid batteries are widely used even when surge current is not important and other designs could provide higher energy densities. Large-format lead-acid designs are widely used for storage and backup power supplies in cell phone towers, high-availability settings like hospitals, and standalone power systems. For these roles, modified versions of the standard cell may be used to improve storage times and reduce maintenance requirements. Gel cells and absorbed glass matte batteries are common in these roles, collectively known as VRLA batteries. Lead-acid battery sales account for 40 to 45% of the value from batteries sold worldwide, a manufacturing market value of about $15 billion. History. The French scientist Gauthierot observed in 1801 that wires that had been used for electrolysis experiments would themselves provide a small amount of secondary current after the main battery had been disconnected. In 1859, Gaston Planté's lead-acid battery was the first battery that could be recharged by passing a reverse current through it. Planté's first model consisted of two lead sheets separated by rubber strips and rolled into a spiral. His batteries were first used to power the lights in train carriages while stopped at a station. In 1881, Camille Alphonse Furet invented an improved version that consisted of a lead grid lattice, into which a lead oxide paste was pressed, forming a plate. This design was easier to mass-produce. An early manufacturer of lead-acid batteries was Henry Tudor. Using a gel electrolyte instead of a liquid allows the battery to be used in different positions without leakage. Gel electrolyte batteries for any position date from 1930s. And even in the late 1920s, portable suitcase radio sets allowed the cell vertical or horizontal due to valve design. In the 1970s, the valve-regulated lead-acid battery was developed, including modern absorbed glass matte types, allowing operation in any position. Electrochemistry. Discharge. In the discharged state, both the positive and negative plates become lead sulfate, and the electrolyte loses much of its dissolved sulfuric acid and becomes primarily water. The discharge process is driven by the conduction of electrons from the negative plate back into the cell at the positive plate in the external circuit. Negative plate reaction. Pb plus HSO minus 4 PbSO4 plus H plus 2E minus positive plate reaction. PbO2 plus HSO minus 4 plus 3H plus 2E minus PbSO4 plus 2H2O. The total reaction can be written as Pb plus PbO2 plus 2H2SO4 2 PbSO4 plus 2H2O. The sum of the molecular masses of the reactants is 642.6 grams per mole. So theoretically a cell can produce 2 faradays of charge from 642.6 grams of reactants, or 83.4 ampere-hours per kilogram. For a 2-volt cell, this comes to 167 watt-hours per kilogram of reactants. But a lead-acid cell in practice gives only 30 to 40 watt-hours per kilogram of battery, due to the mass of the water and other constituent parts. Overcharging with high charging voltages generates oxygen and hydrogen gas by electrolysis of water, which is lost to the cell. Periodic maintenance of lead-acid batteries requires inspection of the electrolyte level and replacement of any water that has been lost due to the freezing point depression of the electrolyte, as the battery discharges and the concentration of sulfuric acid decreases. The electrolyte is more likely to freeze during winter weather when discharged. Ion motion during discharge, H+ produced of the negative plates moves into the electrolyte solution and then is consumed into the positive plates, while HSO-4 is consumed at both plates. The reverse occurs during charge. This motion can be by electrically driven proton flow or Groth-Huss mechanism, or by diffusion through the medium, or by flow of a liquid electrolyte medium. Since the density is greater when the sulfuric acid concentration is higher, the liquid will tend to circulate by convection. Therefore, a liquid medium cell tends to rapidly discharge and rapidly charge more efficiently than an otherwise similar gel cell. Measuring the charge level. Because the electrolyte takes part in the charge-discharge reaction, this battery has one major advantage over other chemistries. It is relatively simple to determine the state of charge by merely measuring the specific gravity of the electrolyte. The Sg falls as the battery discharges. Some battery designs include a simple hydrometer using colored floating balls of differing density. When used in diesel-electric submarines, the Sg was regularly measured and written on a blackboard in the control room to indicate how much longer the boat could remain submerged. The battery's open circuit voltage can also be used to gauge the state of charge. If the connections to the individual cells are accessible, then the state of charge of each cell can be determined, which can provide a guide as to the state of health of the battery as a whole. Voltages for common usages. For the three-stage charging procedure of lead-acid batteries, see UL battery charging. The theoretical voltage of a lead-acid battery is 12 V for 6 kg and 2 V for 1 kg. These are general voltage ranges per cell. Open circuit at full charge, 2.10 V. Open circuit at full discharge, 1.95 V. Loaded at full discharge, 1.75 V. Continuous preservation charging, 2.23 V for gelled electrolyte, 2.25 V for AGM and 2.32 V for flooded cells. All voltages are at 20 degrees Celsius, and must be adjusted for temperature changes. The open circuit voltage cannot be adjusted with a simple temperature coefficient because it is nonlinear. See voltage versus temperature table. Float voltage recommendations vary among manufacturers due to different lead-acid concentration and positive plate grid alloy. Precise float voltage is critical to longevity. Insufficient voltage is almost as detrimental as excessive voltage. Typical charging, 2.37–2.4 V. Equalization charging, 2.5–2.67 V. Charging in sulfated state not accepting small charge current, greater than 3 V. Charging in sulfated state, up to 2.6–2.66 V. Discharging in sulfated state, 1.6 V. Gassing threshold, 2.415–2.48 V for sealed, 2.41 V for PZS, 2.36–2.41 V for GIS, PZV, GIV.